The first thing I wanted to point out to you guys is this, and hopefully you've already seen it up here, but I actually did post it on the front page of our Canvas site, that we have our homework number 1, test review number 1, and you can actually click on right here to get a hard copy of this thing. But you need to go to your modules, homework number 1, test review number 1 up here, and go to modules and scroll down till past section 6.1 here. And you will see right here under test and test review, you click on this guy right here, and you will see, and you can also make another copy of it right here, where here's my directions. This thing is due by Friday, 2 o'clock. You have to get this thing entered in by Friday at 2 o'clock, and you have to turn it in at our review session, or before, it's okay. But remember, our review session is in Fretwell 113 at 2 p.m. So, and if you click on this thing, you can actually see the homework set. So let me click on this guy to talk about this for a second. Here's the homework set. And you'll notice that I'm trying to mimic exactly what the test style is going to be like. And so over here, this is 5.1 through section 6.1. And here are a bunch of multiple choice questions you need to do, and I give you enough space to do the work on it. But these multiple choice questions, all the questions are actually coded into Canvas. So we want to input your answers into Canvas. Now, I gave you, 15 multiple choice questions on this one. Because you guys are the Monday, Wednesday, Friday class, and only a 50-minute class, I probably will shorten the test a little bit off of this thing, so this will be a little bit longer than your test. But what I want you to turn in is just the free response part. Now, even on Canvas, I've coded the free response questions as multiple choice questions, so I'm taking basically 2 grades off this thing. But this is the part, just this part, the free response part 2 of the test review number 1, that I want you guys to actually turn in. So show your work on this stuff, write your answers down, be able to clean it up and the like, and like I said, do all your work with the use, substitution, integration by parts, so forth and so on. Only this, the secondary part, part number 2, is what you're going to turn in. But if you come over back here to Canvas, you should take this thing, print it out, and work it out. And then you need to come over here. I have preview because I'm in charge, but you'll get to submit this thing. You click on this guy here, and you're just going to see that it's going to take you to your Canvas, and it's like a quiz. And here was that first question, but here's the important deal. There's a random generator in terms of the answers on this thing. So even though you printed out a copy that has the answer A, B, C, D, and these are the numbers, we rotate these things around in terms of the answers up here. So just because it's A that you got right on problem number 1, don't click on the first blank. A may be answer down here or something like that. So they do randomly generate. So make sure when you're clicking on this thing that you click on the right guy that you want. Okay? Does that make sense? And even all the way through, even the multiple choice questions, I actually coded, even the free response questions, I've coded as multiple choice. So you can actually give your answers in the entire set. But on that free response, I want you to turn that in so we want to grade your work. I want to see your work be neat, be organized, staple your work together, and turn it in. You can turn it in at Friday's class if you want to. If you can't make the review session, that's perfectly fine with me, but you got to get it to me before 2 o'clock. And the reason for that is, right at 2 o'clock, I'm going to be covering the review session this Friday, and I'm going to go over this homework set. I'm going to talk about the test and strategies and stuff like that, and I'm also going to record it for those folks who can't be there. But I am going to go over that particular homework set with you guys. And because I go over it, and once I hit end, it automatically uploads to the internet. Therefore, the answers are posted, and therefore I cannot accept any late homeworks. You've got to get your homework sets done on time. All right. So questions? Yeah. You had a question? Okay, cool. All right. So we're finishing up today section 6.1, integration by parts, and just remind you of the formula of integration by parts that and when to use integration by parts. The formula that you have memorized is the integral of u dv, that's equal to u times v minus the integral of v du. And when do I use this integration by parts formula I have memorized? I use it, number one, when U substitution doesn't work, and number two, I can view the problem as a product. But if you think about that, everything in the world's a product if you look at them the right way, something times one, but you really want to get that product aspect of it. So if you do have division, you want to bring up whatever in the denominator, you're going to want to bring that up to the numerator, to clean them up, to make it look like a product, so you got your U and your dV, and then you go through your steps, okay? And so this is an offsetting integral. But most important, this is one of my techniques that when U substitution doesn't work, I always try U substitution first. Now, last time we finished up with the lecture, and I was going to do some homework problems for you guys. And so here's our WebWork homework problems. And there's a typo on this one, so take good notes, and because you got a WebWork problem that looks just like this, but of course, we still find typos on this mess, even a couple of years after we typed this thing up. So here we go. It says, quote, use a combination of substitution and parts to evaluate the integral of sine of 3 times the square root of x dx. Now, this is one of those nightmare WebWork problems they give you, because not only do you have to come up with the answer, you've got to follow their direction, their lead, because they're going to walk you through this particular problem, and you've got to answer their blanks to get all the full credit off this thing. So they're going to make you walk through the particular steps on doing this problem. Because this one's a nasty one, because it's a trick. The integral of the sine of 3 times the square root of x dx. Well, first off, they say we either want to use substitution. They say let W, they're not going to call it U substitution, because we're going to use U later. We're going to call it W. W substitution, they're going to let W equal to the angle on the trig function. So they say let W equal 3 square root of x. I don't do square root, so that's going to be 3x to the 1/2 power. But with traditional U or W substitution, your next move is you got to do dW. What is the derivative of 3x to the 1/2? Well, you bring down the power, that's going to be 3/2 x to the subtract 1 negative 1/2 dx. I'm taking derivative with respect to x's. I'm going to clean this guy up. So this means that the dW is equal to 3 divided by 2, and a x to the negative 1/2. Well, 1/2 power is a square root, negative exponent puts them on the bottom, so that's 3 over 2 times the square root of x dx. Okay? And here's your typo on the thing that I promised you guys. It says, it follows that dW is equal to 3 divided by, they forgot the 2 off this thing, 2 square root of x dx. Okay? And therefore dx, and this is what they're going to do on this problem, because remember, this was your correct problem. It was the integral of the sine of 3 square root of x dx. So this is going to turn into the integral of the sine of w, but the problem is I need to substitute it in completely for dx. So I'm going to solve this thing for dx. So when I solve for dx, I'm going to multiply both sides by 2 square root of x and then divide by 3. So I'm even moving the x over here. I'm going to get 2 square root of x divided by 3 dw. And that's what they're saying right here. And of course, 2 fell off of it. So there it is. dx is equal to 2 square root of x divided by 3 dx. And so when I substitute, this goes to 2 square root of x over 3 dw. I'm replacing the dx with 2 square root of x over 3 dw. But I got a problem. I got a big old x in the middle of my w stuff. So the other thing I got to do is this. Well, since w is equal to 3 square root of x, what does that make the square root of x equal to? Move the constant on the side. W divided by 3. So I get to replace this square root of x with w divided by 3. So this turns into the integral of the sine of w times 2 times the square root of x is w over 3 divided by 3 dw. Now I'm going to clean this guy up. This is 2 divided by 3, which is 2/3, divided by another 3, that makes it 2/9. So when you clean this up, this turns into the integral of 2/9 w sine w dw. Now we're ready to fill in the WebWork blanks here. It says this: to successfully continue with the substitution, it is now necessary to rewrite the dx in terms of w. Thus, dx is equal to what? What was dx equal to? Well, dx was equal to dw times 2 square root of x over 3, but the square root of x is w over 3 divided by 3. So when you clean that up, that becomes 2 ninths w dw. And so they want to know this. So when they're solving for the dx, that's going to be equal to some function and times dw. In terms of that function, what is the function equal to? What's the answer? 2w divided by 9. That's what the function in terms of the dw is that the dx is equal to. Does that make sense? Now remember, I solved for dx. So I got over here dx was equal to 2 square root of x divided by 3 dw. But I wanted to replace the square root of x, so the square root of x is w divided by 3. So this is dx is equal to 2 times w divided by 3 over 3 dw. So when you clean it up, dx is equal to 2 ninths w dw. And so the function is actually 2 ninths. That's where it's coming from. Okay? Now, therefore, complete the substitution and get the integral of the sine of the square root of 3 square root of x dx is equal to the integral of g of w dw. When we completely converted this thing over, what was my function that was in front of the dw there? What's my function now? It is now 2 ninths w sine w. That's what it cleaned up to be when you put it all together. So the integral of the sine of the 3 square root of x dx, by letting w equal to the square root of x, you turn this problem into the integral of 2 ninths w times the sine of w dw. So now that becomes my next question. Okay? So here we go. Now, use integration by parts to integrate the integral of that g of w dw. So here we go. I want to integrate the 2 ninths w times the sine of w dw. Now we're going to do integration by parts. Integration by parts is the formula. Integral of u dv equals uv minus integral of v du. And they're telling you, what are you going to let u equal to if dv is equal to, and they told you what dv is, and that would be the sine of w dw. What is the u going to be? Now, I know I always taught you guys, hey, pull the constants out front. But I also mentioned that when I said that, I said, that's traditionally what I do, is I like to pull the constant out front and then I don't worry about them anymore. But this is not me, this is WebWork. WebWork wants you to keep the constant with one of your terms, typically the u guy. So you have to get WebWork credit here, to get the credit on WebWork, you're going to have to put your constant with the u part. So if dv is the sine of w dw, that would make u equal to what? 2 ninths w. Now we're going to do the actual integration by parts. That means du is equal to, the derivative of 2 ninths w is going to be 2 ninths dw. And if the dv is the sine of w dw, what's the integral of sine? 50-50 shot. What is it? All right. Negative cosine. Negative cosine of w. You understand, your life depends on you getting this right. You got to know what the sine of the integral of the sine of dw is. All right, so now plug it into my formula. So this will turn into u times v, which will be 2 ninths w times v, which is negative the cosine of w, minus integral of v, negative cosine of w, times du, which is 2 ninths dw. And I literally just plugged into my formula, and then after I do that, I clean them up. So, cleaning this thing up, this would give me negative 2 ninths w cosine of w. A negative makes it a positive, plus the integral of 2 ninths cosine of w dw. Now the secondary integral, I can integrate that guy. What's the integral of the cosine of w dw? What's the integral of cosine? sine. So this is equal to negative 2/9 W times the cosine of W plus, constant holds over, 2/9, and the integral of cosine of W dW is sine of W plus C. And now just go answer the questions. This gives us, as a function of W, the integral of that G of W dW is actually equal to, and here's my answer, it is 2/9 W cosine of W plus 2/9 sine of W. Now they put the plus C for me. And that's what's going to go in this blank on WebWork. You had to integrate it. But now, remember the question? Oh yeah, the question was, what's the integral of the sine of 3 square root of x? So, what's the last thing I'm going to do is back substitute. Substitute for W, 3 square root of x, and get the actual answer. So my answer is going to be, here we go, this will be equal to negative 2/9. W is 3 square root of x times the cosine of 3 square root of x plus 2/9 times the sine of 3 square root of x plus C. But of course, you know, that would bother me, but leave it like this. 3 goes into 9 3 times, so I would have actually written the answer. Negative 2 square root of x divided by 3, cosine of 3 square root of x plus 2/9 times the sine of 3 square root of x plus C. There is the actual answer to the problem. So this is, again, one of those WebWork problems where you got multiple blanks to fill in during the question because they're trying to walk you through it. Now, everybody in here has a problem that looks just like this guy. You need to go practice it. All they're going to do is change the constant around a little bit, but this is the steps that you need to do to be able to do this problem. And again, most students, they're okay with this problem, but they really hate the idea that WebWork walks them through the steps because they can't seem to get it exactly the way WebWork wants it. If you leave off part of the constant, because I pull constants out front, but WebWork wants to put the constant with you, you have some difficulty with actually getting the right answer on WebWork. The final answer will be right, but you'll miss one of the problems on your steps, and you won't get 100% on this thing. That's the big issue. All right. Here's another one. Again, another WebWork problem. Suppose that f of 5 equals 2, f of 7 equals 6, f prime of 5 equals 9, f prime of 7 equals 7, and f double prime is continuous. Find the value of the definite integral from 5 to 7 of x times f double prime of x dx. Well, this is one of those formula type of problems, but I just want to remind you of something rather. When I integrate the derivative function, what does that give me back? See if you learned anything in chapter 5. What's the integral of the derivative function? The original function plus c, because I didn't put bounds on this. That also means when I integrate the second derivative with respect to x, what is that going to give me? The antiderivative of the second derivative gives me the first derivative, plus c. So, with this problem, the integral from 5 to 7 of x times f double prime of x dx, man, I can integrate this guy if that x wasn't there. U substitution is not going to work because I have no idea what u equal to. But notice if that x was not there, I could integrate the guy. And this is a product, so I'm going to use integration by parts. So here's my formula. It's the integral from 5 to 7 of x times f double prime of x dx. Integration by parts. Integral of u dv equals uv minus integral of v du. I'm going to let u equal to the part I want to get rid of. I wish the x wasn't there, then I could integrate it. So I'm going to let u equal to x, and that would force the dv to be equal to f double prime of x dx. So the derivative of x is going to be 1 dx. However, the integral of f double prime of x dx is what? F prime of x. So as I plug it into my integration by parts formula, it's going to be u times v, that'll be x times f prime of x, minus the integral of v, which is f prime of x, times du, and du is dx. And now, all I got to do is integrate f prime of x dx. Well, I know what that is. The integral f prime of x is f of x. So this is equal to f times f prime of x minus integral of f prime of x dx is f of x. No plus c's on this one. And then instead of putting the plus c, I go back and put the original bounds from 5 to 7. So I used integration by parts by letting u equal x. And then the integral of f double prime of x is f prime of x, plugging into my formula. And then all I have to do is integrate f prime of x, which gives me f of x. And now I'm going to apply the fundamental theorem of calculus. Plug in top minus plug in bottom. So this would be equal to 7 times f prime of 7 minus f of 7 minus 5 times f prime of 5 minus f of 5. Fundamental theorem. Plug in top minus plug in bottom. Now I'm going to start plugging in that information that they gave me. So this would be equal to 7 times f prime of 7. F prime of 7 is 7. Minus f of 7. F of 7 is, there's 6, thank you, 6. Minus 5 times f prime of 5. F prime of 5 is 9. Minus f of 5. F of 5 is 2. So, cleaning this guy up now, plugging in my numbers. 7 times 7 is 49 minus 6 minus 5 times 9 is 45 minus 2. I keep telling you guys, WebWork loves me. So here it is. What is 49 minus 6? 43. Minus, what's 45 minus 2? 43. And therefore 43 minus 43 is, WebWork likes me, 0 is my answer. Trust me, yours won't be 0. You'll be something else. But they just made up some numbers for this thing. But you got a problem that looks just like this. Does that make sense? That leads you guys anywhere? Question? Yeah.
Why did we take in the first part x times f prime of x? Why did we have, since in step before that, the antiderivative is only over the second part of it, why are we plugging in the 7 and 5 in the first part as well? What's the process?
Okay. So, the original problem was the integral of x times f double prime of x dx. So I used integration by parts. I let u equal x and dv be f double prime of x. And therefore, I had to take derivative of x, which is du, which is just 1 dx. And integral of dv is, integral of second derivative is the first derivative. And then I plugged into my formula. So I'm integrating this guy. I didn't worry about the bounds. So this is my u, this is my v, minus the integral of my v, which is f prime, times du. Du is dx. So therefore, the derivative of f prime is f. But instead of putting plus c's, we put a bound. So this becomes x times f prime of x minus f of x. And then you got your bound from 5 to 7. Fundamental theorem, I plugged in top. So this was x was 7, so it would be 7 times f prime of 7 minus f of 7. Parentheses around that, minus parentheses, plugging in 5. 5 times f prime of 5 minus f of 5.
I'm confused about why does the bounds cover the uv part if the antiderivative is only the v du?
No. Okay, the bounds were originally here. So, these were the original bounds, and the goal here is to integrate this whole thing. So if I can't integrate this part, you plug it into this formula. And then you got to integrate this part, and then you get your antiderivative, and then you plug in your bounds on the whole thing. This, once you integrate the secondary integral, will give you the whole answer, and then instead of putting plus c on it, you put your bounds back on it and finish it up by fundamental theorem, plug in top, plug in bottom stuff. All right. Questions? All right. All right. Now, section 6.1 is the last section on your first test, but this is calculus 2, so we can't afford not to continue on and finish the book by tomorrow. So we can move on, even though your test, your homework is due on Friday, your test is on Monday, we're going to move on to section 6.3. Now, I want to remind you, chapter 6 is called Other Techniques of Integration. Now we're going to get specialized in terms of integral types. Chapter 6.3 is focusing on integrating fractions. So this whole section here is going to how you integrate fractions. So now I did this problem on the pre-section video for you guys. Hopefully you watched it and got the quiz done before you came to class today. So this is the whole idea. We're going to be integrating fractions. And here's my problem with it. With traditional integrating fractions, the number one technique is to do U substitution, but when you got a fraction, you want to let U equal to the denominator. If I let U equal to the x squared minus x minus 12, my problem is the derivative is 2x minus 1. And there's no 2x minus 1 inside this problem. Does that make sense? So whatever I let U equal to, du is not in the problem. And the other concept that we're looking at here is, this is what I call a proper fraction. A proper fraction in terms of integrals is when you look at this is a rational expression here, polynomial over polynomial. The degree of the numerator has to be strictly less than the degree of the denominator. This numerator is a degree 1, the denominator is a degree 2. So this is a proper fraction. So we're going to talk about techniques of how to integrate this type of data. Well, again, I went through on the pre-section video and introduced this concept to you guys. So I did this problem. And I did these couple problems, and I introduced more formulas you're going to have memorize to give you an idea of what this section's about. And I did this problem as well using the new and improved, and I'll introduce it to you again, the arctangent formula. So I'm going to pick it up right here, since I did all those problems on the pre-section video there. And I don't typically do those in class unless you pay me lots more money. All right, so here we go. The whole concept here is this idea of partial fractions. Now, let me explain the importance of this whole section. This isn't one of these sections that, I'm going to learn how to do this thing, and when Dr. Taylor tells me, hey, use integration by doing partial fractions on this one, I'll do it, and then I'll be done, and I'll forget it 5 weeks later. No. This is one of those sections that's going to haunt you the rest of your college career, especially for you engineers and STEM majors out here. What we're doing in this section is we're going to be taking big fractions and busting them apart into small fractions. Because the theory of calculus is 'tis better to do calculus on easy stuff than it is to do it on hard stuff. So if I got a big fraction, instead of doing the big fraction, I'm going to bust up this fraction into smaller fractions. This is called partial fractions. You will be beaten to death on this concept in differential equations when you guys get to that level. And other different science classes out there beyond differential equations. But I'm going to really pick on my electrical engineers in here. You guys are going to be taking those classes where you have to solve for circuit classes. And there's going to be a technique that we introduced to you guys called Laplace transforms in differential equations. You are going to be introduced to this concept again in Laplace transforms. So you haven't seen the end of this stuff. This stuff is going to be with you throughout your senior year and then some. So this is a very important concept that you must master. Well, I'm not an electrical engineer, Dr. Taylor. It don't matter. You're mechanical engineers, you're computer engineers, all you guys, you're going to see this stuff again. How many people you guys have to have differential equations? Yep, 95% of the class raised their hand. That's what I thought. You guys are going to see this thing again, and you better master it, because they won't teach you this in DFEQ. They expect you to know it. All right, so first thing you must understand in my algebra review is this. How do you add or subtract fractions? What do you got to have? Common denominator. So this is what we learned in the second, third grade here. We have a common denominator, a over b plus c over d. Your common denominator is bd, and you make it one big common denominator, and you have to multiply the a times the d plus the b times the c, and you make it one big fraction. See, what partial fractions is going to take what you learned in the third grade and go in reverse. You're going to have a big fraction, and you're going to learn how to break it into smaller fractions. And then you apply calculus to the smaller fractions, which makes your life so much nicer. So, just to remind you guys on adding fractions, what is 2 over x plus 1 plus 5 over x minus 4? Well, your common denominator is going to be x plus 1 times x minus 4. And what did you do to the x plus 1 denominator to get the common denominator of x plus 1 times x plus 4? You multiply by x minus 4. So whatever you do to the denominator, you do to the numerator. So it'll be 2 times x minus 4 plus the original numerator was 5 on your second fraction. You had original denominator of x minus 4. To get the common denominator of x plus 1 times x minus 4, you had to multiply by x plus 1. So you write that as one big fraction of x plus 1 times x minus 4. And you get 2 times x minus 4 plus, all your action goes in the numerator, 5 times x plus 1. And then you're going to clean this up by distributing. This will be 2x minus 8 plus 5x plus 5. And then you clean this thing up, and 2x plus 5x is 7x, minus 8 plus 5 is minus 3 over x plus 1 times x minus 4. Just reminding you on algebra, I mean, we're not talking about basic 2/3 times plus 1/3 stuff, but on rational expressions, how to add fractions, or subtract, that is. The other thing you're going to need to know is about factoring quadratics. You know, you've got the anti-fold stuff. You can do factor by grouping, a bunch of different techniques on how to factor classic quadratic stuff. So, especially problems like x squared plus 2x minus 15, you'll see this kind of factoring a lot. How does x squared plus 2x minus 15 factor? X squared is xx. What times what is 15 that differ by 2? 5 and 3, and because it's a minus, they'll have opposite signs. Because the middle terms are plus, the bigger number, 5, will get the plus, the 3 will get the minus. It factors into x plus 5 times x minus 3. Just reminding you of the algebra from high school. Here's another one. What about 6x squared plus 8x plus 2? Well, the first thing you realize is this. When you're factoring, look to see if there's anything in common throughout the entire polynomial, in this case the quadratic. If it is, factor it out. If not, then you can go for the anti-fold stuff here. But you'll notice in this one, 6x squared plus 8x plus 2, I have a 2 in common. Factor that out. That leaves me with 3x squared plus 4x plus 1. And then I can factor that. 3x squared can only factor one way, 3x and x. 1 can only factor one way. It's got to be 1 and 1. And because the last terms are plus, they'll have the same sign. Because the middle terms are plus, they'll both have pluses. And then the last thing I do is I just double check that middle term. And I get the middle term by on the FOIL, the outer inner part. 3x times 1 is 3x, 1 times x is x, 3x plus x is 4x. Yep, this is how it factors. 2 times 3x plus 1 times x plus 1. Just reminding you guys of the good old factor days. The other aspect that you need to focus on, we'll get into later, is the concept of a quadratic of ax squared plus bx plus c, and the discriminant, which comes from the quadratic formula, the b squared minus 4ac part. This is the part that's underneath the square root in terms of the quadratic formula. The deal is when will this guy have an answer, or a real zero or not? Well, you can only take the square root of positive numbers to get real answers, positive numbers or zero. So the discriminant, which is the b squared minus 4ac, must be greater than or equal to 0 to actually get zeros, which means the thing can actually factor. If it's less than 0, you're going to get complex stuff. It won't factor. Does that make sense? So we're going to check using the discriminant here on determine whether these functions are going to factor. For example, the x squared plus 2x minus 15. Okay? So first thing I'm going to do is do the discriminant. Here, a is going to be 1, b equals 2, c equals negative 15. Your discriminant, we call it big D there, is b squared minus 4ac. This will be 2 squared minus 4 times 1 times negative 15. That's going to be 4. Minus 4 times minus 15 will be a plus. 4 times 15 is what? 60. And so it is 64. Don't care what the number is. What's the sign of that number? That happens to be greater than 0, so you are going to have real solutions, which means it will factor over the real numbers. So this guy's going to factor, okay? But look at the next guy. If you happen to have this kind of a quadratic, 2x squared plus 2x plus 8, Yeah, I know you can factor a 2 out of it, but I don't care. I'm going to see if this thing's actually going to have real solutions, which means it'll factor, or if it doesn't have real solutions, means it won't factor. Here, A is going to be 2, B is going to be 2, C is going to be 8. Your discriminant, which is B squared minus 4AC, equals B, 2 squared minus 4 times A, which is 2 times C, which is 8. That's 4 minus 2 times 4 is 8, times 8 is 64, and 4 minus 64 is negative 60. Because it's negative, there's going to be no real solutions, which means does not factor. We're trying to factor things over real numbers here, okay? So this little discriminant can kind of help you gauge whether this thing's going to factor or not. And why do you care? Well, turn the page and you'll discover it. Here's a problem. All right, so again, hopefully you'll watch the awesome pre-section video that I made for you guys on this stuff, and I'm trying to describe the concept, but I'm going to go over it again. Here is a nasty problem. I got the integral of 2x plus 1 divided by x squared minus 3x minus 10 dx. Traditionally, if I was going to integrate a fraction, I would let u equal to the denominator, which is x squared minus 3x minus 10. Then I would take du, the derivative. What is the derivative? 2x minus 3 dx. But with u substitution, whatever I let u equal to, du has got to be in the problem. Do you see a 2x minus 3 in this problem anywhere? Me neither. I got a 2x plus 1, not the same thing. U substitution doesn't work. 1, U substitution does not work. Number 2, this is what I call a proper fraction. I define a proper fraction where the degree of the numerator must be less than the degree of the denominator. What is the degree of my numerator? 1. What's the degree of the denominator? The degree is 2. So numerator is 1, the denominator is 2, the numerator is less than the denominator, proper fraction. And number 3, the denominator factors. So notice this. This is 2x plus 1 over x squared minus 3x minus 10, but that is 2x plus 1 divided by that x squared plus 3x minus 10 factors into x. What times what is 10? That differs by 3. 5 and 2. And minus means they're opposite signs. Middle terms are negative. Minus on the 5, plus on the 2. So it factors into x minus 5 times x plus 2. Does that make sense? So this is your common denominator. What we're going to do with this partial fraction stuff is break this thing up over the different parts of your denominator, the different factors. So the factors were x minus 5, and the other factor was x plus 2. So we're going in reverse. This is the common denominator. I'm trying to break it into smaller fractions. Now here's the deal. This was a proper fraction. So when you have a proper fraction and you're trying to break it into over its partial fractions will also be proper fractions. Proper mean degree of the top will be less degree of the bottom. These factors are degree 1s, right? They're linear terms. What does that make the numerators have to be if they're going to be a degree less than that? Degree 0, and a degree 0 is called a constant. What constants? I don't know what constants they're going to be. I'm just going to call this dude A. I'll call this guy B. But they're going to be constants. They're a degree less than the denominator. Now, your job is to figure out what A and B are. So you do that by, well, there's a couple of different methods. A lot of teachers will teach you guys basically linear algebra, systems of equations, to be able to solve this guy through system of equations. So you're going to run across those professors that when they do it, they do system of equations. They're going to be here about 20 minutes longer than you're going to be here trying to do this problem, because I'm going to show you guys the shortcut method. The shortcut method is the annihilator method. Now, this will give you the answer a lot quicker. When I get you guys into my linear algebra class, I will show you the system of equation stuff. But our goal in here is to be able to get the answer and get it quickly so we can move on and actually calculate the stuff we need. So this is called the annihilator method. All right, I've taken my fraction, I'm busting them up. Now I'm going to take the equation and multiply by the common denominator. My common denominator is x minus 5 times x plus 2. And what I do to one side, I do to the other. What I do to one term, I do to all terms. So every term is going to get hit by x minus 5 times x plus 2. And you're going to get an equation. And when I get an equation, here, the entire denominator factors, you're going to be left with 2x plus 1. That's going to be equal to, here, the x minus 5's cancel. You're left with a times x plus 2. Here, the x plus 2's cancel. You're left with plus b times x minus 5. You got to clear denominators. Now, this creates you an equation. Now, from this, I can do the system of equations and try to compare coefficients. That's traditionally the system of equations method. However, because I cleared denominators, this equation is going to work for all values of x. So you can pick any value of x you want to plug into this thing, and you can get rid of the x parts, and then you get a and b, and you can solve for it. But better than that, because I have a brain, and I got to have two letters I'm trying to solve for, a and b, I got to have two x numbers. I choose the x numbers that completely kill off a term, called the annihilators. So, what term kills off an x minus 5? What value of x? 5. We want to try to make zeros out of this thing. So I'm going to pick 5 and take a wild guess what the other number I'm going to pick is. Very good, negative 2, because that's what annihilates that factor of x plus 2. I'm going to choose negative 2. Now I'm going to plug in these numbers into it. You can plug in it all along the way. Now this is for your benefit, just to show you what I'm doing. This will be 2 times 5 plus 1 is equal to a times 5 plus 2 plus b times 5 minus 5. Clean it up. 2 times 5 is 10, plus 1 is 11, is equal to 5 plus 2 is 7a, plus b times 5 minus 5 is 0, which completely kills off the b term and allows you to solve for a. Divide by 7 on both sides, you get a to be 11/7. And now I'm going to plug in the other annihilator, negative 2. This will be 2 times negative 2 plus 1 equals a times negative 2 plus 2 plus b times negative 2 minus 5. Cleaning this guy up, 2 times negative 2 is negative 4 plus 1 is negative 3 is equal to a times 0 plus b times negative 7. Minus 2 minus 5 is negative 7. So I get negative 3 equals negative 7b divided by negative 7 on both sides, and I get b to be a positive 3/7. Right here is where people will screw this problem up. It's sad. It's called not pay attention. What we're trying to do here is change the big fraction into small fractions. You now know what the values of a and b are. You've got to put them in the numerator of the correct fraction. How many times do I see people find the correct a and they put it over here, and they put the b and they plugged it in for a because they weren't paying attention because they're doing this 90 miles an hour. Take your time. So now this problem is going to turn into the integral of a, because the fraction will turn into a. A is 11/7 divided by x minus 5 plus b. B is 3/7 divided by x plus 2 dx. So instead of trying to integrate a big fraction, now we're going to have to integrate a small fraction. And there are two small fractions. So to integrate two small fractions, basically, you integrate each one. Integral of 11/7 divided by x minus 5 dx plus the integral of 3/7 divided by x plus 2 dx. Now, I mentioned this to you guys before. The ultimate goal in Chapter 5 and Chapter 6, as we keep cranking it up on you guys, is to get you guys to have the ability to integrate in your head. This is not a rule I have memorized, but it is a u substitution. And what would you let u equal to? Look at that first integral. What are you going to let u equal to? Denominator, x minus 5. What's du? dx. 11/7 is a constant. I ain't worried about him at all. This becomes the integral of 1 over u du. What's the integral of 1 over u? Natural log absolute value of u. So you end up getting 11/7 natural log absolute value of x minus 5 plus the next guy, u substitution in your head. What's the integral of 3/7 divided by x plus 2 dx? 3/7 natural log absolute value of x plus 2 plus c. and you got your answer. That is actually the integral of that original fraction, which was 2x plus 1 divided by x squared minus 3x minus 10 dx. Does that make sense? Okay? All right, look at this problem. I want you to integrate x minus 1 divided by x plus 1 times x squared plus x plus 1 dx. All right. Notice I'm trying to integrate, and it's a proper fraction. The degree of the top is 1. What's the degree of the denominator? What's the degree of the bottom? 3. You actually have to fold it out. X times the x squared makes it x cubed. It's actually a degree 3. But the degree of the denominator is bigger than the degree of the numerator. The degree of the numerator is less than the degree of the denominator. We're good to go. And it's a proper fraction. And the denominator factors. They went ahead and factored it for us. Merry Christmas. But here's the deal. As I mentioned to you guys before, when you have, x plus, some kind of a number as a factor down here, what did the numerator have to look like to be a proper fraction when you bust this stuff up? It's got to be a constant. What if you happen to have a quadratic in your denominator? An x squared plus, some kind of a number times x plus some kind of another number. Okay, number 1, number 2 there. This is a quadratic. The numerator has to be a degree less than the denominator. This guy now is a degree 2. So what does the numerator have to be 1 less than degree 2? Degree 1. And a degree 1 would look like linear. Linear meaning it would look like bx plus c. And you got to put the bx plus c. If your denominator was a cubic, some kind of x cubed plus some kind of a number times x squared plus some kind of a number times x plus some kind of other number there. You got a bunch of different numbers going on this guy here. This guy's a cubic. Do you know what your numerator has to look like? A quadratic. Not just x squared. It's going to be ax squared plus bx plus c. The degree and all the terms less than that have to be there. This is your model for being a proper fraction. Does that make sense? So, in this problem, I have x minus 1 divided by x plus 1 times x squared plus x plus 1. You should recognize that x squared plus x plus 1 does not factor. I can't factor that guy. Okay? So, you can also do the discriminant on it if you want to look at it, but you guys should know 1 times 1 is 1. I'll never be able to get a x in the middle of this thing when you try to pull it out. So, this is going to be equal to, breaking it up, x plus 1 plus, the other factor is x squared plus x plus 1. Since this is a degree 1, what does the numerator have to be? A constant. So degree 0, a constant. I'm going to call that A. Since this guy is a degree 2, the numerator has to be a degree less than that. That means it's got to be linear, degree 1. That we'll use different letters. I'm going to call it bx plus c. So far, so good? This is how this fraction is going to break up. Now, I'm going to multiply by my entire common denominator of x plus 1 times x squared plus x plus 1. This will completely kill. It'll leave me with x minus 1 is equal to a. Here the x plus 1's cancel. You're left with x squared plus x plus 1 plus the bx plus c times the x squared plus x plus 1's cancel. You're left with x plus 1. I cleared denominators. Question for you. How many letters do I have to solve for here? 3. So I need 3 x numbers. What x numbers do you choose? Well, look at your factors. I got a factor of x plus 1. What's a good number? -1. The problem is that is the only factor there that actually has a 0 that will knock it out. So now I need a couple of numbers. These are not going to be annihilators. They're not going to kill any terms off, but they'll help me out. Now, you can plug any number in this thing you want to. You can plug in 107, 45, 4 nights if you want to. Knock yourself out. But I got a brain. You know what numbers I'm going to choose? That's right. 0, and next number will be 1, and after that maybe a 2 or a -1. I'm going to pick nice, easy numbers to plug in, and 0 especially because it's easy to plug in. So, But honestly, it won't matter what numbers you use, but always use the annihilator number first. So when you plug it in, minus 1 is minus 2 is equal to a times negative 1 squared is 1, minus 1 plus 1, that cancels, you're left with times a, plus b times negative 1 plus c times negative 1 plus 1 is 0. That completely kills off, and you're left with a equals negative 2. Now I'm going to plug in 0. And I typically do this rather quickly. Plugging in 0, you get 0 minus 1, which is negative 1, equals a times, let's see here, 0 squared plus 0 plus 1 is 1a, plus b times 0 plus c times 0 plus 1 is 1. B times 0 goes away. So you are left with negative 1 equals a plus c. B times 0 went away. It didn't annihilate it. I got a system of equations, but always use your annihilators first. Because a is negative 2, you can plug it in. Negative 1 equals negative 2 plus c. Add 2 to both sides. I get c to be equal to 1. Now plug in 1. 1 minus 1 is 0. Is equal to 1 squared plus 1, which is 3. 3a plus b times 1 plus c times 1 plus 1 is 2. I'm going to distribute. So I get 0 equals 3a plus 2b plus 2c. I now know what a and c are. Plug it in. 0 equals 3 times negative 2 plus 2b plus 2 times 1. 0 is equal to negative 6 plus 2b plus 2. Negative 6 plus 2 is negative 4. 0 equals negative 4 plus 2b. Add 4, 4 equals 2b, b equals 2. Now I've got my numbers. I go back and rewrite my integral as a is negative 2 over x plus 1, plus b is 2, x plus c, which is 1 over x squared plus x plus 1 dx. It turned into a simpler problem. This guy is real easy to integrate. What is the integral of negative 2 divided by x plus 1? Negative 2, natural log, absolute value of x plus 1. The question is, how do you integrate this second guy? Well, what's your number? The denominator doesn't factor. What are we going to do when it doesn't factor? Well, I got other stuff to cover in this section when we get there. But this one, your number one technique is what? Always. What would you let u equal to? X squared plus x plus 1, the denominator. And you just happen to notice what's the derivative of this guy? 2x plus 1 dx, which is in the problem. So this thing turns into 1 over u du, and that's equal to the natural log absolute value of u, which is the natural log absolute value of x squared plus x plus 1. So this becomes plus the natural log absolute value of x squared plus x plus 1, and don't forget one big plus c. This secondary interval was great because it was a u substitution. Does that make sense? We're going to be looking at a lot more of these type of partial fractions, but the idea of taking big fractions and bust them into small fractions, that's what I'm going to do on Friday, and then at the review session, I'm going to go over your homework set and prepare you for your test on Monday. So study hard, and I'll see you guys on Friday.